Code is written, unit tests pass, and the application works locally. But pushing that software to production without dedicated security testing leaves the door wide open. A bad actor can exploit a single oversight to access your database or bring the entire application down. This diagram outlines a DevSecOps approach to that problem. By integrating 3 distinct security gates, SAST, SCA, and DAST, into the development lifecycle, we can identify vulnerabilities before they reach the end user. First is SAST, or Static Application Security Testing. This is where automated tools read through the raw source code of an application to identify insecure patterns, like hard-coded secrets or SQL injection risks, before the software is even built. Next is SCA, or Software Composition Analysis. Instead of looking at your original code, SCA scans the third-party dependencies your application relies on to ensure you aren't pulling vulnerable libraries into your project. Finally, there is DAST, or Dynamic Application Security Testing. This acts like a real-world hacker. It doesn't look at source code. Instead, it attacks the running application, making thousands of API calls to uncover configuration or runtime errors. Layering these 3 processes together creates an automated security net. Let's look at how to deploy and run each of these tools locally. We start our static analysis by spinning up the free community edition of SonarQube. Running this command deploys it as a background Docker container, exposing it on your local host via port 9000. If port 9000 is already in use on your machine, you'll need to map it to a different host port. While the community version catches many common patterns, enterprise environments often use paid versions to scan for more complex vulnerabilities across larger codebases. Before scanning your application, you need to configure the connection. Create a new file in your project directory and name it exactly sonar-project.progredies. A common mistake is to make project plural. If you add an S, the tool won't recognize it. With the configuration file saved, run the sonar scanner CLI command. This reads your local source code and pushes the analysis directly to your SonarQube container. Once the CLI finishes, open the SonarQube dashboard in your browser. The Security Hotspots tab reveals flagged code segments requiring a developer's attention. Looking at the report for a vulnerable Python file, SonarQube highlights exactly where a weak randomizer is used for cryptography and flags potential cross-site request forgery risks directly at the line level. By identifying these structural logic flaws before a single line is compiled, SAST serves as a primary defense in the development cycle. Even if your original code is spotless, the packages you import might not be. Developers routinely install a handful of direct dependencies, like Flask or requests, to save time. This branching structure shows how those direct imports work. A single package might rely on 50 others, and each of those relies on dozens more. A handful of installations quickly multiplies into thousands of indirect dependencies, any one of which might contain a known exploit. To secure this web, activate a Python virtual environment for your project and run a software composition analysis tool. For Python, you can install and execute pip audit against your requirements file. The CLI output lists every discovered vulnerability in your entire dependency tree. It flags outdated packages with critical severity tags and provides specific CVE numbers so you can research the exact threat on national databases. Manually verifying the security of 100,000 lines of third-party code is impossible. Automated SCA tools handle the math, identifying risks in your supply chain that humans would overlook. With the code and library secured, we move to the runtime environment. For this step, deploy the OWASP Juice Shop application, a mock e-commerce platform built with intentional security flaws, on port 3000. To test it, spin up the OWASP Zap container. Using its CLI, we point the Zap tool directly at the local URL of our running Juice Shop. As Zap initializes, it blindly fires thousands of varied API requests at the application. It maps out the user interface, probes the endpoints, and attempts to force errors, acting like an attacker scanning for weaknesses. Unlike SAST or SCA, Zap has no access to the actual source code. It only knows what the running application exposes to the outside world. Once the scan completes, Zap generates an HTML report. Reviewing the results reveals vulnerabilities that only appear when the application is active, like missing content security policy headers or severe CORS misconfigurations. Clean code can still be compromised if the environment deploying it is improperly configured. DAST provides a vital reality check, identifying weaknesses in the live configuration that static analysis cannot see. Scanning generates a lot of data, and not every alert requires immediate action. By cross-referencing CVEs on the National Vulnerability Database, engineers can prioritize real threats and manually mark false positives as safe inside the UI to keep the reports clean. This flowchart maps tool integration into a standard CI/CD pipeline. Committing new code automatically triggers SAST and SCA scans in parallel. Passing those checks deploys the code to a staging environment, which triggers the DAST scan to attack the live build. Because we use CLI commands to run these tools, they generate standard system error codes. If a scan detects a critical vulnerability, the command fails, the pipeline breaks, and the build is blocked from reaching production. We've analyzed logic for internal flaws, audited a third-party dependency tree, and dynamically attacked a live environment. You now have the exact Docker setups and CLI commands needed to run these tests. Apply them against your own non-production applications to generate your first automated security reports. Integrating these automated fail-state security gates ensures that known vulnerabilities are identified and blocked long before your code reaches an end user. Mastering these 3 pillars is the foundation of becoming an effective DevSecOps engineer.